we will start this lecture 22, and if we recall that we discuss about the what you call combustion wave, under which we discuss about both deflagration and detonation. If you remember that we derived expression for a basically combustion wave, on which we learned about weak detonation and weak deflagration, which can occur in nature. But however, the strong detonation and strong deflagration will not be occurring in nature. Of course, one can simulate in the laboratory, but generally it is not that easy to simulate as well. Today, what we will be doing, we will be basically concentrating our discussion on the deflagration, that is basically the premix flame. When you talk about premix flame, we always interested to look at what really will be the structure, that means inside what is really happening. Because if you recall that in the last lecture, we did not really bother about structure of the flame. We assume there is some heat release rate, and then we use this conservation of mass, momentum and energy equation, derive the expression for what you call various properties like pressure, density, other things. But today we will be looking at one dimensional premix flame, and if you look at one dimensional flame can be obtained in the laboratory, but in natural it is quite difficult to have that one dimensional flame. Of course, if you look at the premix flame is basically a man-made flame, you can assume, as I told that Bunsen had found out that flame. And of course, one can assume, because you can stabilize in a burner, and then one can assume it to be one dimensional. Therefore, similarly in the we can use one dimensional burner and then establish a flame which can assume to be one dimensional. Keep in mind that here what we will be discussing is laminar one dimensional premix flame, right. But in nature, most of the flame will be turbulent in nature, and also in the practical situation it will be turbulent. So therefore, it is important to look at turbulent flame, but however, due to its complexities and other things we will not be looking at, because we can relate this laminar flame to the turbulent flame, particularly when we will be moving to the gas turbine combustors. Then I will be discussing or touching upon that turbulent premix flame to some extent, but not really, because it is a quite complex subject to be dealt in this lecture, in this course. So, if you look at what you observe, whatever from here I have plotted here in this vertical axis temperature, mass fraction of fuel and oxidizer. If you look at this is basically mass fraction of the reactant. Reactant can be fuel, can be oxidizer, and of course, there will be a product. And if you see this, that it is decreasing, that means it is consuming this mass fraction of the fuel, and also you can have a similar plot for the variation for the mass fraction of oxidizer. It need not to be same, but it will be similar. And if you look at what you can observe here, that in this zone the gradient is very high, and not only for the mass fraction of the reactant, but also for the temperature. Temperature is being shown here, right. And there is a lot of heat being released in this zone. If you look at this red one, heat being released, peak value, and then it receded toward that. And of course, there will be some intermediate reaction which will be occurring, reactants, and the reaction will be occurring, and some of the reaction will be occurring in this region. So, if you look at the flame can be broadly divided into three categories. That means, flame in the sense flame zone, right. This zone can be broadly divided into preheat zone, reaction zone, and recombination zone. what is really happening in this preheat zone? If you look at, temperature is not really going up, but a little bit slowly increasing in this zone, because why? There is a negligible heat release. If you look at heat release is very small in this domain alone, of course, with that temperature also shoots up. So, negligibly small heat release is occurring, and certain chemical reaction do take place in this zone, which I have not shown. Maybe some of the like species like HO2 or HO or something will be occurring in this region because of temperature being little bit shooting up. But however, like it is not that. If I compare this preheat zone with the life of a human being, what it would be? Nothing really is happening productively. So far flame is concerned. Flame is basically what, where the exothermic reaction will be taking place. If you look at overall in this zone particularly, overall reaction, whatever it will be occurring, it will be what you call net effect will be nullified. That neither exothermic nor endothermic, temperature is remaining constant, but in this case there will be little bit increase. So, this will be similar to your what you call student life, where you are being prepared to do a productive work during your adulthood, right, kind of things. So, but whereas all this gradient, gradient is occurring, or the temperature heat being released in the reaction zone. Of course, the zone in this there will be several species which will be liberated radicals, and that will be radiating various spectrum of the light which you can see. For example, Cs star, OH, and then C2 star and other things. I discussed those things. Cs star will give a blue, and then shoot if it is the yellow, and then some purple color, all those things will be coming. So, you will see that. And keep in mind, this is the reaction zone which is very thin as compared to the preheat zone. And in the, if you look at, that means in the reaction zone most of the chemical energy is released in the form of heat, right, in the reaction zone, and decomposition of course will take place, and this decomposition really not take place in reaction zone, it takes place in the beginning of the reaction zone or just before the reaction zone, because there will be pyrolysis products of the decomposition of the fuel. Like for example, propane will be converted into methane, some other things, and then goes on like that. So, that will be creating some radicals to be what to call be consumed in this reaction zone. And that is very important, because whenever I see a flame, I always feel it is a life, like life is getting flame is getting burnt, like fuel is being getting burnt. So, also in life you getting burnt your time, time is receded as you go on, and you get prepared to contribute for the life which is not being done through education nowadays, right. But in principle it should be like a flame, it prepares the species to be consumed in the reaction zone, and then it will release heat and also the light, so that it will be people can take help. So, reaction zone is very important. So, also the productive life of a human being, one should not be really only worried about his food, he should worry about what he can contribute for the others. So, reaction zone, as I told, it is very thin as compared to the preheat zone, and keep in mind that this is the very critical part so far analysis is concerned, and because the gradient is very high here, right, and temperature gradient and concentration are high as I told you. And recombination zone, this zone particularly is basically the recombination zone, where I have shown here temperature should be almost flat, there is no change in the temperature along with the x direction. If I say this is x direction, then there is no change, but in real situation, particularly for a hydrocarbon, this thing, there will be some recombination, like carbon dioxide and water will be formed, and some amount of heat being released, particularly for hydrocarbon. As a result, the temperature profile will be increasing towards the asymptotic value, which I have not shown deliberately, because I want to simplify and then analyze it, right. So, if you look at, you summarize, the flame zone can be divided into three categories, one is preheat zone, reaction zone and recombination zone. And you should be careful about this, because what we will be doing, we are not bothered about this recombination zone when we will be analyzing, and this one dimensional flame, we will be bothered about preheat zone and reaction zone. What is really happening here, one has to look at it. Like if you look at the various processes that are occurring, like if I look at the thermal side, then there is a conduction, there will be convection, there will be also radiation, heat transfer will be taking place, and some chemical reaction will be taking place, and it will be preparing the fuel and oxidizer to be burnt in the reaction zone. So, of course, in the recombination zone, as I told you, the no heat release in this zone is being occurred for our case, but in that, but whatever the heat release being occurred in real situation is very, very negligible small as compared to the in the reaction zone, right. For the practical analysis purposes which we will be doing, keep in mind that this is our as I told you, is a reaction, the full flame, and if I look at along with x direction, when x is very far away, that means x is infinity. What will happen to temperature? Because temperature profile I have shown here, temperature gradient will be dt by dx will be 0, right, yes or no. And this is, I am starting from here, okay, this is my origin. So, towards, if I go towards away from the origin towards the left hand side, this will be minus infinity, right, the x is equal to minus infinity. What will be the temperature then? Gradient, it will be again dt by dx is 0. Similarly, for mass fraction of fuel, oxidizer, will be valid, this condition will be valid. And keep in mind that we are saying that in this reaction, this is the reaction zone where the T ignition will be there, which is closer to the Tf. That is again an assumption we are making, but it is not bad. That means Tf minus Tiz is very, very small. This assumption will be using for analysis, for actually deriving a relationship for burning velocity. If you look at this flame front will be moving with the SL burning velocity towards unburned mixture. This is unburned mixture, right, am I right? And this side is what? Burned mixtures, right. So, we will make certain assumptions before really looking at the equations and simulating it. So, what are the assumptions which are very simple, which we have done? One dimensional, steady, inviscid, laminar flow, because we are talking about laminar flame theory, right. We want to understand and derive a relationship for laminar burning velocity, right. And this burning velocity is with respect to what? With respect to unburned mixture, right, because it is moving towards the unburned mixture. So, we will take that with respect to it is moving, right. So, and flame is quite thin, that is an assumption we are making, right, and it will be dependent on what? The thickness of the flame will be dependent on what? That is a thing we should worry about. Will it be dependent on the fuel air, type of fuel and type of oxidizer, or will it be dependent on the fuel air ratio? Will it be dependent on inlet temperature? Will it be dependent on inlet pressure or the pressure? What it would be is a one question might be lurking in your mind, right. So, but we are assuming the flame to be thin. Thin, of course, we know it is like a surface. So, we will see that an ignition temperature is very closer to the flame temperature, right. We have this an assumption, and no heat loss including radiation we are assuming. Is it possible there will be a flame when there will not be any radiation or there will not be any heat loss? Heat loss, I mean we are saying it, there will not be any radiation. Of course, it is possible provided it is flame, like dividing of the some spaces, like there are two kinds of radiation. One is gas phase radiation, other is solid phase radiation, if suits are there, but we are assuming there is no soot in this flame, okay. So, therefore, that is negligible, and their gas phase radiation will be very, very small, but in real situation radiation will be there, you cannot really eliminate it or avoid it, but we are assuming it to be having no effect on the analysis. Pressure difference across the flame is negligibly small. You can invoke that what we have done in the last lecture about combustion wave and look at it, that you will find the pressure difference will be very, very low, right. Therefore, we will not be considering the momentum equation. Why it will be low? Because it is a deflagration, but if it is detonation, we cannot really manage to have this assumption, we cannot. So, we will not be considering momentum equation, and then keep in mind that we are assuming the binary diffusion, which will be and also Fourier and Fick's law will be valid, right. Because binary diffusion, why we are saying that we will be talking about a what you call a single step chemistry here, and if it is a multi step chemistry which are supposed to, I mean naturally it will be occurring in the flame, then this assumption won't be valid. For the simplicity we are assuming, and constant transport properties we are assuming, which is not true, because the temperature is going from TU will be what, it will be around 300 Kelvin and T flame will be around 2200 Kelvin for hydrocarbon air flame. So, it is quite a bit. So, you cannot really have that Cp particularly you will be varying with temperature. So, also the diffusivity, I mean like conductivity, and then mass diffusivity, D is the mass diffusivity and Kg is the conductivity of the gas will be changing, but we are assuming for the simplicity. And unity Lewis number, that we are assuming. What is the meaning of Lewis number? Lewis number is basically is alpha by D. The alpha is the thermal diffusivity, that means alpha is basically Kg by rho Cp. Kg is the conductivity, rho is the density, Cp is the specific heat, that is known as thermal diffusivity, and D is same as the D, that is the mass diffusivity, right. That we are assuming 1. What is the meaning of it? That is saying that your species equation and the temperature equation or the energy equation will be similar. If it is 1, I can substitute those values and get that. If I get a solution for 1, other I can get very easily, but that is again restricted case. It is in reality it is not the possible, but we will be doing that, I mean all the thing. And the mass conservation, if you look at, is a one dimensional flow. So, we can get d by dx, rho Vx is equal to 0. What is the meaning of that? It is meaning is that mass flux is equal to the rho Vx is constant. What is the meaning? Is saying that rho u, if I say, and then SL, SL is the burning velocity, rho u is the density. So, basically all these analysis what we are doing, we are interested to derive a relationship for burning velocity, and that comes from the mass conservation. If you look at, we will be basically looking at this burning velocity as L to find out. So, and as I told you, we are using a single step chemistry model for this, that is 1 kg of fuel reacting with nu kg of oxidizer going to the product of nu plus 1 kg of product, right, P. And therefore, we need to look at this species equation for fuel, oxidizer and product, right. Let us consider the species conservation equations as I have enumerated here for fuel, oxidizer and product, and these equations are basically similar, and let us consider the species conservation equation for fuel, which having 3 terms. First is your convection term, that is rho Vx dxf by dx, which will be equal to the diffusion term and the mass consumption term, consumption of fuel, mass consumption of fuel. And if you look at this diffusion term is rho d square xf divided by dx square, and keep in mind that this diffusivity what we have considered is binary in nature, That means, this diffusion between two spaces, whereas in actual system multi-component diffusion would likely to take place. And these equations will be similar for the oxidizer. For example, there will be convection term rho V x dx O x divided by dx is equal to rho d square x O x divided by dx square, and mass consumption of the oxidizer. And keep in mind that this is per unit volume, this mass consumption of oxidizer, even the fuel, everything, all this term is basically per unit volume. Similarly, we can get the what you call the product, that is the convection term, that is rho V x dx p divided by dx, which will be equal to the diffusion term and the mass generation of the product. The diffusion term will be rho d square x p divided by dx square, and the mass consumption of the product we have considered as we have taken in the global kinetic scheme, that is the 1 mole of fuel is reacting with nu mole of oxidizer, which will going to the nu plus 1 what to call gram of product. So, therefore, we will have to solve these equations and to get this each mass fraction of fuel and oxidizer and product. So, energy equation will be having similar form, that is rho V x C p dt by dx. This is your what you call convection term, and this is your conduction term, and this term is your what you call the heat generation or heat release, right. That means H f I not m dot I f, I can be fuel, in this case oxidizer and product. So, let us look at how we can expand this term and see this term particularly. So, if you look at we are looking at this 1 kg of fuel reacting with nu kg of oxidizer going to the product of nu plus 1 kg of product. So, we can write down that m dot triple dash f, that is the mass of fuel per unit volume being consumed, is equal to 1 over nu m dot triple dash O x is equal to minus 1 over nu plus 1 m dot triple dash p. Why minus? Because this fuel and oxidizer is being consumed, whereas product is being formed, right. Instead of writing minus here, I have put here. So, it is okay. So, if I do that, like let us look at how we can do. I can expand this term H f I m dot I can write down H f I H f f o plus m dot triple dash f, right. And similarly, I can write down for oxidizer and for the product. If I substitute these values, like for oxidizer, what it would be, m dot triple dash O x will be nothing but your nu plus m dot triple dash f. So, that is this term, right. And similarly, from here I can get to this term. If I take this m dot f out, what I will get? I will get H f plus nu H f oxidizer minus nu plus 1 H f product, and that is nothing but your heat of reaction. This is your heat of reaction, right. So, what is eventually it is coming, that those things will be very easy to look at that, right. I can express in terms of that. So, now what we will be using, as I told you, that we will be only considering the energy equation as the Lewis number equal to 1. Once we solve that, we can really look at how this fuel or the oxidizer mass fraction changing with respect to the x axis or along the length of the plane, right. So, that can be and that is a very important assumption, which we will be discussing about when we will be in detail when we are discussing about droplet combustion, and that is we will be using one known as Swab-Jeldovich transformation, that we will be doing. And here I am dealing little different way. right. So, I want to give both flavor, this is more what you call physical and that is more mathematical or mechanical. So, let us look at this energy equation becomes m dot Cp dt by dx is equal to kg d square dt by dx square minus the heat release term. What you could observe here? What kind of equation it is? I need to solve this equation 8. Could you observe? Is it possible I can solve this equation? It is a second order equation or not, right? And it is a non-linear and coupled equation, right? Yes or no? Can you really solve? Is it possible to solve with your OD? You have learned about this is the OD, ordinary differential equation. Can I really solve this equation? Because if you look at m dot triple dash f, right, how it will be? Look at Arrhenius form of equation, that is m dot triple dash f. If I look at even global kinetics, it will be AF, then CF, concentration of F. Of course, you will have to in terms of mass fraction, if you want to put it, you will be talking in terms of molecular weight also multiplied into C of oxidizer, E power T E by R T, right. So, if you look at this term is a very non-linear term, because I should know the temperature, I should know the activation energy, I should know the pre-exponential factors, and those activation energy pre-exponential factors, right, will be dependent on what is the fuel air ratio you are talking about, and also it will be dependent on temperature, very highly temperature, because E power to the E minus R by RUT. So, therefore, it is you do not know temperature, therefore, you are solving this equation, therefore, it is quite difficult to do that. So, how to go about, we will see, we will go back to this diagram. If you look at what we are doing, I mean basically what we will be doing to solve this equation, because it is a quite complex non-linear, and what we will be doing, we will be basically looking at in the these zone, in the preheat zone, which is more predominant here, there will be convection, and if you look at this equation, convection and conduction. But however, the heat release term will be negligibly small, because this is a very small portion, right. That will be very small portion, right. This is very small portion, right. So, we can neglect that, and in some zone what we will be doing, we will be basically looking at in this zone, in the reaction zone, where we will be neglecting the convection. That means, whatever heat will be released will be carried away by the conduction, because the temperature gradient is very high, right. So, the gradient is very high. So, therefore, we can neglect that term, right. So, that is the way which we will be looking at it. And I have already told you that this is your what you call at x is equal to minus infinity dt by dx 0, and x is a positive infinity, that far away dt by dx will be 0, is a very away from that, right. So, and what are the boundary condition? If you look at, of course, I have already talked about it, t is equal to t u x minus infinity dt by dx 0, x positive infinity, it will be t is equal to t f dt by dx 0. And as I told you, we will be looking at this preheat zone. In the case of preheat zone, this will be 0. In this case, this will be 0 in the preheat zone. For preheat zone, this will be 0. Therefore, you will get m dot Cp dt by dx kg dt square by dt x. That means, the whatever the conducted like heat is coming from the reaction zone, it is being balance between the conduction and convection, right. Through conduction is coming and it is convected away, right, that is the balance. So, it and if you look at for the preheat zone, the of course, these are the condition has to be valid, that is of course, at the x will minus infinity, t is equal to t u dt by dx 0, x is equal to minus x ignition, that I have showed you at that point t is equal to t ignition. See, basically you want to decouple this equation and solve, divide and rule basically, but you are landing in one problem. I do not know this T ignition, I do not know, you are trying to solve, but you are landing in problem. So, how to do that we will see little later on. So, if I what to call integrate this equation, what I will get dt by dx ignition is equal to m dot Cp kg T I z minus T u, right. I am just integrating this equation by integrating equation 9 by integrating equation 9, right. We can get dt by dx, right, because the other term it is 0. So, that is going away, right, and then you are getting m dot Cp kg T ignition minus T u, right. So, in the reaction zone, however, what will happen in the reaction zone, what we will be doing, we will be basically looking at this convection term will be negligibly small, only the conduction and the reaction will be there, right. It is small means it is small as compared to the contribution of the heat release heat and whatever being conducted, that way. But you cannot really say it is not there, but we are just assuming. Then if what I will do, I can write down here multiply dt here, I can multiply dt, right. If you look at what is this term will be coming as what to call, it will be coming as dt by dx whole square, of course, provided if I multiply this time left hand side 2 and this time right hand side 2, then you will get this term as that, right. So, then if I just do this, I will get dt by d ignition is nothing but 2 delta Sc by kg integrated m dot f over the T ignition to Tf, because this range is T ignition is one side and other side will be Tf, right, because that right. So, as a result you will get it. So, but still use this expression over here, equation 10 and 13 we can club, because this is T ignition and this is dt by dx ignition, right. This equation will be same, this right hand side of equation 10 will be same as the right hand side of equation of 13, right. Then we will do that. So, that we are avoiding this gradient, temperature gradient at ignition point, right. So, that is the way we are doing. So, combining this equation 10 and 13, we are getting m dot double dash Cp by kg T I z minus T u equal to root over 2 delta Sc kg integrated over m dot triple f dt. It is integrated over T ignition to Tm, right. So, if you look at, still we are not solving, because we need to integrate this, integration that is not really possible, because you do not know the temperature, how it is varying with temperature, right, and the T ignition is also not known. So, you will have to do some approximation for that, and of course, I can simplify this m dot dash is equal to kg by rho Cp 1 over this, just rewriting this equation 14 in this fashion, nothing more than that. So, we know that m dot double dash is nothing but rho u S L from the continuity equation. So, I can write down over here, I can write down rho u S L is equal to this, right. So, then I can really look at combining this equation 15 and 16, I can get S L is equal to kg by rho u Cp, because rho u has gone over here and rest of the things are same as that of the equation 15, right. Now, what we need to know, but still you know that here I have introduced Tf minus Tu in place of T ignition and Tu, right. What we are assuming that T ignition minus Tu is approximately 3 by 4 of Tf minus Tu, right. If you look at what I am doing, right, this is my T ignition, this x direction, this is your Tu and Tf. What I am saying, T ignition minus Tu, right, this portion is nothing but 3/4 of Tf minus Tu, right, and that is fair enough to say that, but this is ad hoc, okay. There is nothing sacrosanct about it, but we are looking at flame temperature profile from experiment and approximating it and doing that, right. This may not be valid for limit mixtures. It may be valid for the what you call stoichiometric, where the reaction will be governed by the activation energy, right. So, therefore, there it will be valid, whereas for the limit mixture it cannot hold good, nor even for hydrogen air, where the activation energy is very, very small, it will not be valid. So, this is the limitation of this kind of analysis. So, then still we are having a problem with this m dot triple dash f dt by Tf, but we can assume that mean fuel burning rate per unit volume will be m dot f triple dash. That means, this term I am saying that is nothing but m dot f triple dash average over the region what is happening, because it is changing, this mass burning is changing in the region from here to here. If you look at this zone, it is changing, it is like coming over here, this is your m dot f, right, it is changing reaction rate, in other words, right. But here we are saying no, we are not bothered about integration, we will say it is average. What is that average? That will be approximated as the what you call a reaction rate, Arrhenius form of reaction rate, right. Right. What is that? Molecular weight of the fuel, AF, CF, N1, C oxygen, N2, e power to the E by R UT. And if I know these values AF, E, and then concentration of that, which will come from the what is the fuel air ratio, I can estimate this thing, right, provided I know this temperature, right, and that temperature will be doing some average one kind of things, right. So, expression for burning velocity, that means that is equation 16 becomes what, like if you look at what I will do, I am taking this kg by rho Cp inside. So, therefore, it will be square inside of square root, 0.5 is nothing but square root, okay. And then I am taking also 4 and 3. So, 4 it is 16 into 2 32, and 3 square is 9, I have taken inside 9, and kg is already there, and Tf minus Tu whole square, because this term I am taking inside the square root. So, it will be square, but we can look at this delta Sc and whether we can express in terms of temperature. That can be approximated as delta Sc is approximately nu plus 1 Cp Tf minus Tu. So, what we will be doing, instead of this I will be writing down Cp nu plus 1 Tf minus Tq in place of this, okay. So, what will happen, then this Tf will be cancel it out, right, the only one Tf will be there, and this portion, right, this what it would be, this will be m dot triple dash f average, this equation, okay. Yes or no. So, I can write down, and if you look at what is this one kg by rho Cp, that is nothing but alpha thermal diffusivity, right. And if you look at kg and there is a Cp, so if I look at what is alpha, alpha is nothing but kg by rho u Cp. So, Cp by kg will be, if you look at this is alpha square, alpha, right, I can write down basically this kg will be alpha rho u Cp. So, in place of this I can write down as alpha rho u Cp, this Cp will cancel it out, that this rho, because this is a rho basically. So, this will be cancelling it out and rho u will be there, right, because this is nothing but your what, alpha square, right, alpha. So, therefore, I will get SL is equal to 32 alpha divided by 9 rho u nu plus 1 m dot f triple dash. This is a very elegant expression, but if you look at how many approximation we have done and what is the sanctity of those approximation, one has to worry about. But however, we are getting a closed form solution, right, and that is we can see. So, from this what you can see, that burning velocity will be dependent on the nu, that means fuel air ratio, right. nu is the stoichiometric ratio in our equation. It will be dependent on the thermal diffusibility, right, that means properties Kg, rho u and Cp. It will be dependent also on the temperature, that is the reaction, and density is there means it will be dependent on the pressure as well, right. So, we will see how it is varying, and right. So, that means SL, if you look at SL is a function of what? Unburnt temperature, it will be equivalence ratio, it will be pressure, and what else? Also the if it is additive is there, I can say inert gas, we will be seeing that, right. What else it can be? Type of fuel air mixtures, because this m dot triple dash will be different for the different fuel air, like hydrogen oxygen, hydrogen air, methane oxygen or propane air, it will be different. So, it will be dependent on also the type of fuel oxidizer system, right, fine. So, these are the things we will see that. Now, let us look at effect of equivalence ratio, that means these are the all, if you look at this is the CH4 air and laminar burning velocity in the vertical direction, in the horizontal direction equivalence ratio is being plotted. Equivalence is fuel by air divided by fuel air stoichiometric. If you look at this will be methane air is having this line and it is decreases on the lean side, because this is your stoichiometric. So, this is the lean, right, this is the reach, and of course, for if you look at propane air, right, then it will be a little higher values, but it will be similar in nature. So, if you look at for hydrocarbon air, 25 to 50 is the peak value, because this is around 37 kind of thing peak value, this is around 40, 42, even some mixtures will be there 50 kind of. But however, acetylene, this is C2H2 is acetylene, is also an hydrocarbon, but is exception, where it is having a very high velocity, high burning velocity, but its peak value does not occur at the stoichiometric. See, this occur not really stoichiometric, but little bit around that 1.05 around that it occurs, which where for the general hydrocarbon, methane, propane, butane, pentane, like that, okay. But for except acetylene air, where the peak value here will be occurring, in somewhere this side, right. And as I told you, for hydrocarbon air, it the peak burning velocity occur at 0.015, and hydrogen air mixture, which I have not shown in this diagram, right, it is a very high values, peak burning velocities occur at phi is equal to 1.8, right. And similarly, for of course, for the CO air, you can see the phi peak value is occurring around 2 kind of thing. And if there is another very important thing, you should know that SL is proportional to the molecular weight inverse. That means molecular weight, what you call increases, the burning velocity will decrease, right. And that is the reason why maximum SL burning occurs under fuel rich condition. That is the one reason what people are talking about. As I told you, CO air mixture, the maximum occurs under the fuel rich condition, right. And CO air burning velocity data is not really understood due to the complex kinetics. Still it is remaining, why it is so, what is the reason, how it can be, why it is occurring this way, right. And peak burning velocities for hydrogen, C2H2 and CO air, occurs as the reside, cannot be explained in terms of molecular weight. So, still yet to be, explored and found out why it is occurring this. So, let us look at effect of initial pressure and temperature on the burning, what you call burning velocity. So, if you look at SL, SL is basically we have derived that 32 by 9 alpha by rho u nu plus 1 into m dot f triple dash average, right. What is saying? That is, if I look at this alpha, alpha is basically proportional to temperature power to the 1.75, and inversely proportional to pressure. That means, if pressure increases, alpha will decrease, that way. So, and whereas m dot F triple dash rho u, it will be P power to the n minus 1, because the P n comes from the what you call the concentration and minus 1 from the rho u, right, and of course, temperature dependence is there, right. Now, if I look at this SL is the what you call will be dependent on this n values. N is the overall order of global chemical reaction, right. N is the overall order of reaction, like kind of things. So, then SL is proportional to P power to the minus n minus 2 divided by 2, right, because why it is coming to is a square root, therefore, divided by 2. Okay. So, this relationship is supported by the experimental data, right. These n values will be varying for reactions like hydrocarbons and depending upon fuel air, mixture ratio and other things. So, let us look at how it is being supported, and this value, this is what you call is basically m. This is known as pressure index, right, that is m being plotted. Pressure index m is plotted here with respect to SL. When the burning velocity is in certain range, in this range, if you look at in this range, what you are getting? You are getting that pressure index is negative, right. That means, it will occur when n is less than 2, then m will be negative, right. That means, it will be not second order reaction, but rather it will be maybe 1.5, 1.4 or something like that. N is 2 means what? Second order reaction, right. N is less than 2 means it is less than second order reaction, right. Keep in mind that this is not elementary reaction, this is a global reaction. Okay. And in elementary reaction, you really can't get these fractional values, okay. That is also important. So, then what you are getting for a hydrocarbon flame when n is there and which will be occurring less than 50 kind of things, 20, 30, 40, 50, yeah, this is 50, right. What do you see? The m is negative. What is the meaning of that? That means, when pressure is what you call decreases, what will happen? The burning velocity will increase, right. Why? Because this is a negative value, right. If pressure is decreases, then SL will increase, or pressure will increase, then SL will be decreasing, right. So, this is the term where, and whereas n is equal to 2, then what happened to m? M is almost remaining constant. If it is constant, right, it is 0, that means the burning velocity is independent of what? Pressure. Burning velocity will not be changing with respect to pressure, and which will be occurring in this region, right, where m is equal to 0, and that will occur only when n second order reaction, that means reaction is second order. But however, in real situation it will not be, okay. In the sense I can't say it will not be, but in certain regime it may occur, but in certain regime it will be different, right. So, when n is greater than 2 for a hydrocarbon flame, particularly when SL is greater than 100 in this regime, right, then what happens? That m is positive. So, therefore, the burning velocity decreases with decreasing in initial pressure. So, what you can draw a conclusion? You can draw a conclusion that burning velocity will be varying with respect to pressure depending on the order of reaction or depending on the system what you are talking about, right. So, let us look at how it is varying. If you look at these variations and other thing, you will find that temperature is basically affecting the burning velocity. With increase in temperature, the burning velocity increases, which I have shown here for methane air flame, and the m values will be varying from 1.5 to 2 kind of thing. That is the relationship you can get. Generally, it increases with respect to the inlet temperature, right. So, let us look at effect of inert additives. Like if I look at this, there are 3 additives one can think of for a methane air flame, and laminar burning velocity is plotted with respect to the percentage of methane in the mixture. You can see that when it is nitrogen, the burning velocity is very low, around 30, peak value is around 36 or 37 centimeter per second. But when you go for, and it is drooping down both the lean side and the reach side, right. This will be lean side, lean, and this is the reach mixture kind of thing. And similar observation you can get that burning velocity is changing with the percentage of methane in mixtures for the argon and helium, right. But as you are substituting this nitrogen with the argon and helium, the burning velocity is increasing, but the peak values also is not in the same place, it is shifting towards the right, that means more fuel. So, if you look at this observation, there is a reduction in burning velocities when you are coming from helium to argon to nitrogen, right, and narrowing this flammability limit. Of course, this is the mixture where between which burning velocity will be there, you can have combustion, beyond which there will not be. So, it is narrowing as you are coming from helium to the nitrogen, and shifting of the peak burning velocity I have already discussed. But why this is there? Because addition of inert gases changes the ratio of thermal conductivity to specific heat. Like it is burning velocity is coming alpha, the thermal diffusivity, right. So, this is a similar thing is occurring, resulting in change in the burning velocity. And burning velocity with helium addition is higher than the argon and nitrogen. Question arises why? Because there what will be happening, the molecular weight will be changing, because these are all heavy, nitrogen heavier than the argon, argon is heavier than the helium, So, with this molecular weight being what you call reduced, therefore, burning velocity is increasing, like burning velocity is proportional to the mW minus 1. If you look at that is coming from your reaction rate, right. You remember that reaction rate m dot triple dash f average mW, there is a root over. So, therefore, it is coming from that, right. And argon nitrogen have almost same thermal diffusion, and the same heat release, argon attains higher flame temperature than the higher SL. So, therefore, you will be getting that. And with this we will stop over, and we will continue discussion in the next lecture, right.